Hi everybody, I hope this video finds you well. In today's video, which will be the first actual content video starting the official content of our course, we'll be taking a look at section 6.1 from your textbook, which introduces you guys to the area between two curves. This is a very natural extension of what you sort of finished up with in Calc 1 or in Math 190, where you were introduced to the concept of a definite integral and measuring the area under a curve. So this is a sort of very natural jumping off point and a great way to sort of start off our course by taking a look at this section 6.1. So section 6.1 is all about determining the area between two curves. So before we get into discussing that, let's just recall a little bit of what you guys had sort of seen back from Math 190. So we want to recall the following fact from Math 190. If we have f of x a continuous function on some interval a to b, remember that to be integrable, meaning that you can take the integral of something, all the function needs to be is continuous. Remember, being continuous is a weaker condition than being differentiable. Being continuous just means that there are no sort of breaks in the curve. It doesn't necessarily have to be smooth. It could have some sharp corners. That's fine in terms of being continuous, in terms of being integrable, but that would not be okay for being differentiable. So our assumption is we've got a function that is continuous on some interval. Then the definite integral, which we write the integral from a to b of f of x dx, gives us the signed area under the curve f of x. Now, there's a couple things I want to mention from this. First of all, just to make sure that we sort of understand, we illustrate this. This is basically saying if we've got some axes here, and then maybe we have some function like this, call that f of x, and maybe that's from a and that's b, and we're talking about that we have that this is continuous on that interval. Right? Then that integral a to b f of x dx, right? That gives us the sort of shaded area under that curve and above the x-axis. So this guy equals that shaded area there. Equals that shaded area. Now, if we want to say a little bit more, where did this actually come from? Well, this actually came from the concept of a Riemann sum, which was basically that we came up with a bunch of approximating rectangles. So we had some rectangles that sort of looked like this, maybe more like this if we were doing sort of left end point approximation, something like that. And then we let those rectangles get infinitesimally thin, meaning that their width basically approaches 0. And it turned out that that infinite Riemann sum is equivalent to the definite integral here. So that's where this sort of came from back in 190. The only reason I mention that is because we're going to be investigating a lot of things that sort of involve those Riemann sums and everything. And something I just want you guys to sort of think about here is that since we're integrating sort of dx, the way you should envision this shaded area being sort of mapped out in this integral is if you think about infinitesimally small rectangles, what you're really thinking about is you're thinking about a bunch of sort of vertical lines, right, at each individual x value. And as we go along, right, they each stretch up to the curve and down to the x-axis, and then those vertical lines, which are basically infinitesimally thin rectangles, that's what's actually filling in that area, and that's why we get that shaded area under the curve and above the x-axis. The only other thing that we should mention maybe from this definition in terms of just recalling is that remember that the definite integral measures what we call signed area. Signed area is a little bit different than like geometric area. When you guys were taking like geometry courses or things like that, and you learned about area, you sort of learned that area in terms of a physical idea, like the area inside of a circle or the area enclosed by a fence or something like that, always has to be a positive number because area as a geometric or as a physical idea must be positive. When you're looking at a definite integral, though, it gives you signed area. And basically what we do is we consider that areas above the x-axis are viewed as positive area, whereas areas below the x-axis are actually considered negative area. So it is possible that a definite integral, even though it's measuring an area, could come out as negative, right? Just to sort of illustrate that, right? If we had something like this, right? If we had some curve, say, like that, maybe that's our f of x, and here's a, and here's b. Then if we were looking at this guy, right, and we're talking about the integral here, if we were to measure integral a to b f of x dx, then what we would be mapping out, just to use some different color here, is we'd be mapping sort of this shaded area here. Again, just using those vertical lines to remind you that we're doing things dx here. Eventually, we'll be starting to do things with respect to other variables. And it would be this shaded area, and just as a note, it would be negative in this case, right? So the shaded area would actually be considered a negative area because it's below the x-axis. And remember, that can lead to some weird cases. You could have a function, I won't draw this fully out, but you could have something, maybe like a sort of sine curve that looks something like that, where the positive area, where that sort of positive area here matches the negative area there, so that the overall definite integral comes out as 0 because the positive and negative areas are canceling out. So just remember that a single definite integral is mapping signed area. Could be positive, could be negative, right? It's a little bit different than geometric area. But that's the main idea that sort of concluded your Calc 1 introduction, was that you can use that definite integral to measure the signed area under a curve. We're going to be turning our attention to trying to determine the geometric area between two curves. And we're going to do that, again, by making use of these definite integrals. And to be honest, a lot of the applications in general in this course, in Math 191, are going to be learning how to use definite integrals to measure a whole variety of different areas, volumes, and other geometric constructs that come from functions and curves. So let's take a look at that. So this is going to be your sort of main idea for the area between two curves. So what we're going to do is we're going to suppose that we have two continuous functions. So now we're going to have two functions because we're talking about two curves. Again, we have to assume that they are continuous here, so that we can actually assume that they have an integral, right? Remember, to be integrable, you need to be continuous. So we've got two functions, and we're going to assume that they're continuous on this interval a to b. We're going to make a further supposition here that one of the functions, f of x, is greater than or equal to the second function on that interval entirely. In other words, visually, this means that like one function is on top of the other for the entirety of the interval. Then the area, notice that we're saying the area here, meaning sort of the geometric area, not the signed area, but literally the geometric area, meaning it's always positive, between these two curves, i.e. below the function f of x and above the function g of x, can be found using this definite integral, the integral from a to b, f of x minus g of x dx. So let's give a little explanation about why that sort of makes sense. So let's set up our situation here. By assumption, we've got two functions. So let's assume that we're working from some a to b, some arbitrary a to b. I don't know, let's say that that's f of x there, and maybe that is g of x there. Okay? And we're trying to determine the area between these. Notice that I'm allowed to sort of draw my picture like this because we know we're working on this interval a to b. I know that my functions are both continuous, so they don't have any breaks or anything in them. And I'm supposing that one of the functions, f of x in our notation, is strictly greater than the other for the entirety of the interval, so I can put one safely on top of the other for the entire interval. And we're trying to measure this shaded area between these two curves. So we're trying to measure the area between these two. So the idea sort of is based on using what we know from Math 190, sort of from our basic definite integrals. So let's go ahead and first consider this integral. If we think about the integral from a to b of f of x dx, well, what do we know that that measures? Well, that would measure the area under that f of x curve. So that would measure sort of all this stuff. And it should be pretty clear that that is too large, right? That contains all of the stuff that we're trying to measure, but it also contains this stuff down here, which we're not trying to measure. But if we then think about the integral from a to b of g of x dx, well, that would be all this stuff down here. Right? That would be exactly all the stuff under the g of x curve from a to b. So the idea then is that the sort of black shaded area, which is really the area between curves, well, if we take all of the blue stuff, which is all of this stuff here and all of this stuff here, and we subtract the red stuff, which is just the stuff down here, then what's going to remain is just the stuff in between. So in other words, the sort of black shaded area is actually the integral from a to b f of x dx minus that integral from a to b g of x dx. And then the idea is that since we know that integrals distribute over addition, subtraction, constant multiplication, we can combine this into a single integral. So we can then say that this is equivalent to the integral from a to b f of x minus g of x dx. And notice that that's exactly the expression that's stated up here. So this gives you guys just a little visual explanation of where this equation or where this formula is coming from. Now, the only thing that you guys should keep in mind that's sort of a limitation to this, and we'll explore this further as we start to do examples, is that there is one major assumption here. I mean, we are assuming that the functions are continuous, but that's a necessary assumption because if they weren't continuous, you wouldn't be able to integrate. But the second assumption is that one of the functions is strictly greater than or equal to the other on the interval. In other words, one function is always on top of the other, right? And visually, when we're talking about on top, since we're integrating with respect to x, and we're drawing those vertical lines, on top literally means vertically on top. You can see that g of x, if you were standing here on the x-axis and looking up, g of x is on bottom, f of x is on top. So we have to make sure that f of x is larger than or equal to g of x on the entirety of the interval. As we'll see later on, we'll start running into some examples where that's not the case, and we'll need to divide our interval into several pieces, one where f of x is larger, and then maybe one where g of x is larger. So we'll take a look at that. All right, now that we've developed this idea, let's take a look at a couple computational examples and get a sense of how to do this. So let's go ahead and start by trying to work through this example here. We're going to try to determine the area of the region formed by the curves y equals e to the x, y equals 1 over x equals 1, and x equals 2. Now, we could try to just jump right in and solve this, but it's going to be pretty hard to do that because we don't necessarily know which function is on top, which is on bottom. Is one always on bottom? It is always a good idea when doing these area type questions. Pretty much actually everything we're going to be doing at the beginning here in Chapter 6, we're always going to want to have at least some rough sketch or diagram of what's going on here. So let's give ourselves an axis. We can pretty much just focus on the sort of positive x values because we can see that that's going to be sort of what's important. Let's call that x equals 1, and let's call that x equals 2. Again, we don't have to be super careful about scale or anything. We're just trying to get a rough diagram. So let's think about what y equals e to the x looks like. So I guess if we're thinking about, there's maybe, we'll give ourselves some points here. If we're thinking about from x equals 1 and x equals 2, that means e to the x is going to go from like e to e squared. We know e is like 2.7-ish, so that means it's going from about like 2.7 up to a little less than 9. So I don't know, we can just give ourselves a scale of like 2, 4, 6, 8, 10. Again, we're just being sort of rough here, right? So that e to the x is going to sort of start somewhere in here, and then it's going to go somewhere that e squared, maybe somewhere up in here, right? And again, that's going to have that sort of exponential look. If it came through, it would be something like that, and it'll continue up there. And probably not a bad idea to label those sort of ends here. We know that this guy is technically at 1 comma e, and this guy here is at 2 comma e squared. And this, of course, in general is y equals e to the x. All right, then let's look at this y equals 1 over x. We know at x equals 1, that's going to be at 1 there. And then at x equals 2, it's going to be at 1/2. So it'll look something like that. And that curve is looking something like that. If we continued it on, it would have that vertical asymptote at 0, and then it's got a horizontal asymptote that way. But there we go. We can again label those points. What do we have there? That's going to be 1, 1, and then this guy here is going to be 2, 1/2. And then, like we said, we can just zoom in a little bit to see that a little more clearly. And then we've got two other curves that we want to draw on here, x equals 1 and x equals 2. Those are both vertical lines. So there we go. There's our x equals 1, and there's our x equals 2. And you can then see by using these four curves, there's only one sort of region that makes sense that's defined by these four things. It's this stuff right in here. So we're trying to determine this shaded area in here. right? Because this is the only thing that makes sense in terms of being the area of the region formed by these curves. So the stuff sort of below this, above this, between these two values here. Now, is one of these functions exclusively on top for this? Yep, that e to the x is on the interval from 1 to 2, always larger than 1 over x. So we should be able to do this pretty safely here. So we can say that that shaded area here is going to be equal to the integral. Our bounds are going to be going from 1 to 2. So we're going to be doing from 1 to 2. And then the function that is on top exclusively is that e to the x. And then minus the function that is on bottom exclusively, which is that, oh, we didn't actually write it on there, my apologies. This guy down here should have been y equals 1 over x, minus that 1 over x dx. And again, just for not really, necessary on this one because the region's pretty simple, but how are we actually getting that shaded area? Well, since we're working dx, we're sort of thinking about vertical lines that go from here down to here. So what we're really doing to shade this thing in is we're sort of filling in vertical lines between those two curves, and then that's filling in that entire region there. And those vertical lines start from e to the x, and they only go to 1 over x rather than stretching all the way down to the axis. If we didn't include that minus 1 over x, then we'd actually be shading in all the stuff below e to the x all the way down to the x-axis. But by removing that minus 1 over x, we're removing this stuff down here, and we're just getting the stuff in between. In terms of actually evaluating this integral, this is pretty easy. We can just integrate directly. So this, if we integrate, is going to become e to the x minus ln absolute value x, because we know we can just integrate each piece separately. Integral of e to the x is e to the x. Integral of 1 over x is ln absolute value x. We can put our evaluation bars 1 to 2. Remember, since it's a definite integral, no need for that plus c there. Now we can just plug in the endpoints. Looks like we should get e squared minus ln of 2, and then minus e to the 1 minus ln of 1. Notice that I can drop the absolute value because 2 and 1 are already positive values. And not much we can really do with this, but I suppose there's one brief simplification. We can call this e squared minus ln of 2 minus e, and then of course the ln of 1 is just 0, so we can drop that. A couple things you might want to just check just to make sure you sort of understand some of the theoretics behind this. If you type this into a calculator, you can confirm that this is indeed positive. It has to be because we're talking about the actual geometric area between these, so this is guaranteed to be a positive value. Another thing computationally you can check, notice that by having our picture here, we knew visually that e to the x was always on top of 1 over x. If you want to confirm that sort of computationally, choose any value you like between 1 and 2. So pick your favorite number between 1 and 2, maybe like 1.3 or 1.75 or whatever. Plug it into e to the x, plug it into 1 over x, and you will see that the e to the x is always larger than the 1 over x, which confirms that on this interval, that e to the x function is larger or is the top function on that interval. Okay, there we go. We've done our first example of determining the area between a couple curves defined on these things. This is the simplest possible case because what we had is that the question itself gave us the bounds. It told us about x equals 1. It told us about x equals 2. It gave us the two functions. And on that interval, from 1 to 2, one function was always on top of the other. This is the simplest possible case. The other examples we'll be doing, we'll see that we'll start to introduce some extra complexities. So let's go ahead and take a look at those. So our next example is we're going to try to determine the area of the region formed by the curves y equals the absolute value of x minus 1 and y equals 2/3 x plus 1. So this is a slightly more complicated one, maybe partially because of the absolute value there. We're not usually as comfortable working with the absolute value function, but that's not really the reason that this is a more complex example. The real reason is that notice the information here is a lot more limited. Back in this example, we were given the two curves and we were given the boundaries. Here, we're just given the two curves. But actually, that gives you a sort of hidden piece of information. To actually form a region, this tells us that these curves must intersect at some point. There's got to be some intersections here, or else the region isn't going to be well defined, right? If the region just extends infinitely, then the area is going to be infinite. But there's got to be some intersections here to actually close it off and make it a well-formed region. So it's your guys' choice whether or not you want to start by trying to draw out a sketch or if you want to find the points of intersection first. Let's see if we can just find those points of intersection to start with. So let's see if we can find points of intersection. All right. So to find points of intersection between two curves, you got to set the curves equal to each other. So we have to do absolute value of x minus 1 equals 2/3 x plus 1. Might have been a little while since you solved something that involved an absolute value. So remember, what you're going to do is you're going to sort of split this into x minus 1 equals 2/3 x plus 1. And there's going to be one where you use the negative of this as well. Negative x minus 1 equals 2/3 x plus 1. So in other words, we use one where we're imagining the positive half of that absolute value and one where we're using the negative half. Then we can solve these. So looks like this guy should give us 1/3 x equals 2. Yep, and then we should get x equals 6 there. So yeah, we have x equals 6. And then on this guy here, we can go ahead and solve that. We get x minus 1, negative 2/3 x minus 1. Looks like we get x equals, if we add the 1 over, negative 2/3 x. And then it looks like we just get, what is that, like 5/3 x equals 0, so x equals 0. So we've got two possible points of intersection. Technically, when solving absolute value equations, you should check that these actually work. There is the potential that you get like extraneous solutions, so let's just check. Plug in x equals 6. Over here, you're going to get absolute value of 5, which is 5. Over here, 6 divided by 3 is 2. 2 times 2 is 4, plus 1 is 5. Okay, that works. And x equals 0. Over here, you get absolute value of negative 1, which is 1. Plug in 0 here, you get 1. It really does work. So, if we wanted to go a little bit further, I guess when we were doing that too, we can actually think about the points of intersection. This point, when we plug in 6, like we were saying, we get 5, so that's going to be 6, 5, and here we get 0, 1. So those are our points of intersection. This also tells us a little bit about where we probably want to sketch our graph. So let's go ahead and sketch our graph. Once again, we're going to sort of focus over here because we sort of know the x values that are going to be important are sort of 0 through 6. So we'll just go 0, 1, 2, 3, 4, 5, and 6. And then it looks like 1, 2, 3, 4, 5. And doesn't really look like we're going to need too many negatives. Absolute value x minus 1. Absolute value of x in general looks sort of like that V shape. That minus 1 is a horizontal shift to the right. So we sort of know the point of the V is going to be here. And then we know that it's going to be here and here, there, and I suppose we can just jump all the way down to where it's going to be about there. So there's our absolute value function. So there's y equals absolute value x minus 1. Obviously, I could continue to draw it this way, but since I already did my points of intersection, I sort of know the relevant information is over here. And then I can go ahead and draw this guy, 2/3 x plus 1. That's just a line that has slope 2/3 and intercept of 1. So it starts here. Then we know it intersects there. So it looks like it's going to be something like that. And I guess technically he would continue that way too. We'll just put the little arrows indicating. And there we go. That's y equals 2/3 x plus 1. And now that we've drawn this, we can clearly see this guy would continue this way. There's sort of that V shape. And then this arrow here continues that. They're not going to have any other points of intersection. We just found these 2 points there. I think I'll just go ahead and draw. Not really necessary to put those in, but anyway, there we go. So we've got our diagram there. We want to try to determine the area here. So we're looking for this stuff in here. Okay. So we now know the bounds. We're going to be going from x equals 0 up to that x equals 6. And luckily, we are in the nice situation where that line, y equals 2/3 x plus 1, it is exclusively on top for the entirety of the area. So we know that the top function is going to be that 2/3 x plus 1, and the bottom is going to be that absolute value. So let's go ahead and write that out. We can say that our shaded area here, this is where we're taking a look. Our shaded area is going to be equal to the integral from 0 up to 6, because we're starting from 0, 1, 2, 3, 4, 5, and 6. And then we can go ahead and our top curve is that 2/3 x plus 1, and then minus our bottom curve, which is absolute value x minus 1 dx. All right, so if we were just interested in writing down an expression for the shaded area, this would be it. But we actually want to evaluate it and try to figure out what this is, which also probably means that we need to remember how you actually evaluate integrating an absolute value function. Well, the problem is you can't really integrate an absolute value function directly. Instead, you want to split it into sort of two pieces. And as you guys know, when you're working with an absolute value function, it changes at this moment where you switch from one half of the v onto the other. So we're going to have to break this into a couple different pieces. So this tells us then that our shaded area here is actually going to be the integral. We're going to start from working on this half here, the 0 to 1 piece. So 0 to 1. On that 0 to 1, the line is still the top, so we're still going to have the same top part, 2/3 x plus 1, minus, on this part though, if we think about it, this is where x is less than 1. This is where this is going to be negative, so the absolute value is actually going to apply a negative sign. So we're going to have minus negative x minus 1 dx. And then we're going to have to add to that the integral. Now on this portion, from 1 up to 6, still have the same top function, 2/3 x plus 1, minus, now, since we're on the positive half of the v, where x is above 1, meaning the absolute value isn't going to do anything, we can just put x minus 1. If you're a little unsure about this, or you didn't have many examples in 190 of integrating absolute value functions, another way to sort of think about this, just as sort of a side note here, we can just put this as a note over here. What we're really doing is we're remembering that this guy can be defined as a piecewise function. We are really saying that x minus 1 in absolute value can be thought about as negative x minus 1 when x is less than or equal to 1, and it can be thought about as x minus 1 when x is greater than or equal to 1. So we're using that as a piecewise definition, and then we're integrating each piece separately. And notice we're splitting our integral at the moment where the sort of piece of the absolute value changes. Okay, now we can get out of using the sort of blue here, right? This is a much better expression because it actually is in stuff that we can integrate. So let's go ahead and integrate that real quick. So our area here, I don't really like this SA. Eventually we'll talk about the surface area, so let's just say area here. Okay, so let's go ahead and get that. We don't have to keep using blue at this point. So we have the integral from 0 to 1. Oh, we can simplify a little bit. That looks like it's going to, those negatives are going to cancel out. So it looks like we're going to get like a, 5/3 x dx, and then plus the integral from 1 to 6. In here, we're going to be subtracting. So that looks like we get a minus 1/3 x, and then plus 2 dx. Then we can go ahead and actually integrate that. This guy is going to become an x squared, and then we'll divide by that 2. So it looks like we get 5/6 squared from 0 to 1. And then over here, same idea. Looks like we should get minus 1/6 squared plus 2x, evaluated from 1 to 6. Plugging in that, looks like we should get 5/6 minus 0. And then in here, if we plug in the 6, looks like we should get, when we plug in the 6, we're going to get 36, and then times minus 1/6, so that's negative 6, then plus 12, and then minus what happens when we plug in the 1, minus 1/6 plus 2. And if we simplify all that, 5/6 plus, what is that going to be there? It's going to be a 6, and then a 4, so it looks like 4 plus 1/6. And looks like overall, yeah, it's going to come out pretty cleanly. Looks like we should get an area of 5. So the area of this sort of shaded region here is actually equivalent to 5. Now, you might ask yourself, was there sort of any clever ways to do this? Well, we could have actually maybe figured this out geometrically, since this is a straight line and since the absolute value is made of a couple straight lines. This is actually a triangular shape, and if you go through and you use some geometry and you figure out this length here and you figure out this length here, you can go ahead and, since this is a right angle, you can just use your sort of standard area of a triangle formula. But, oh, there we go. Not too bad to go ahead and do this. So what were the main points of this example? Well, two things really. One is in terms of actually understanding the region. Bounds were not given, which implied that there had to be points of intersection, which we found algebraically. Use those to sketch ourselves a nice graph. Then we were still in the sort of easier case where one curve was always on top of the other. So we could write the integral as one curve minus the other. Only trouble was that one of the curves was an absolute value, so we did end up having to split just to have a better understanding of those absolute value functions and actually be able to integrate. All right, let's take a look at one final example here. All right, so we're going to try to determine the area of the region formed by this curve here, x cubed minus 3x squared plus 2x plus 1, and y equals 3x minus 2. Now, once again, we're in this situation where the bounds are not being told to us, so we know that there must be points of intersection. So let's start with that. We can do our points of intersection, and then we'll get into graphing it. So with our points of intersection, we've got to set these equations equal to each other. All right. Pretty easy to bring these guys onto this side. So x cubed minus 3x squared minus x plus 3 equals 0. This is cubic. People don't really like solving cubics too much. I suppose you could use rational roots and say that any of the rational roots would have to divide into 3, so you'd have to have things like 1, -1, 3, -3. You could also do this guy by some factoring via grouping. So we could factor out an x squared, get an x minus 3 there, factor out a -1, and then get an x minus 3 there. So grouping does work. We pull out that x minus 3, we get an x squared minus 1, and then it looks like we could factor that a little bit further, x minus 1, x plus 1. All right, and it looks like we're going to get 3 points of intersection, x equals 3, x equals 1, and x equals -1. In terms of points, we can plug these into either equation. Probably easier to just plug them in here. So it looks like the points of intersection are going to be 3, 7. 3 times 3 is 9, minus 2 is 7. Looks like 1, 1. Plug in 1 there. 3 minus 2 is 1. And then looks like also -1, -5. Plug in -1 there. -3 minus 2, going to be that -5. So this gives us a sense of where we'd like to draw this thing. We're sort of drawing it from -1 to 3 in terms of the x. And then for y's, it looks like there's going to be stuff going on from about -5 to -7. So we'll give ourselves a larger sort of axis on this guy. So we've got sort of 1, 2, 3, 4, 5, 6, and 7. And then 1, 2, 3, 4, 5, 6, and 7 there. And 1, 2, 3, 1, 2, -3 there. Okay. I'm going to actually start by drawing the y equals 3x minus 2 one, because that's a line. That's a little bit easier. We know that that guy is going to be at -1, -5. So 1, 2, 3, 4, 5. So somewhere down here. Then we also know that he's going to go through that 1, 1 there, and then that 3, 7 up there. So there's my linear. Okay, that's the y equals 3x minus 2. And then we should draw this guy. Now, I know that this guy goes through the same points, but it might not be clear. You know, we know cubics can sort of look like that. So we can plug in some other things. We can sort of say, like, at x equals 0, this is going to be at 1 here. So we know that he's actually going to go from here to here. Then I'm going to actually hit this. A little bit nasty, so maybe we could try, like, if we just are a little unsure, we can always use some table of values here. So x and y equals x cubed minus 3x squared plus 2x plus 1. So like we said, at x equals 0, it's going to be 1. That's nice and easy. But I would like to sort of know what happens in between these guys. So I guess I could do something like 1/2 and get like, what, 1/8 minus 3/4 plus 1 plus 1. So that's a little bit messy, but that looks like a quarter, 1 1/4, which is 5/4. I guess we can just make common denominators. Oh well. So that's 1/8 plus a fourth plus 1, which is 8, 10, 11 over 8, which is a little bit bigger than 1, so I guess somewhere in here it's sort of like that. And then it might be nice to know sort of what it does over here. So I don't know, let's plug in like 2. So that's going to be 8 minus 12 plus 4 plus 1. That looks like -4, so it's going to be at about 1. So it's going to be like here. So I guess it's sort of reasonable to think that this guy comes up like that, down like that. I suppose it's got to turn around somewhere like there. So we sort of know it's going to come like that. And there we go. So you can see that we're in a more interesting situation here because over here, right, we actually have the cubic on top, right? The cubic is on top here. But then at this moment right here, the cubic actually switches to being underneath. So we're going to need 2 separate integrals to handle this. And again, just to shade in, the region that we're sort of going to be interested in is this stuff here and this stuff here. Also notice that we do have some stuff like below the x-axis, but that's not going to be of interest to us here because we're determining an area of a region, which is geometric. So we're really measuring from here down to here. So everything's still going to be viewed as positive here. All right. So how are we going to do this here? Well, we're going to have to first begin by starting from here and moving to here. So, you know what? To just make it a little bit easier visually, I'm going to shade in this other portion using a different color. So we've got sort of 2 things we need to determine so you guys can see what integral corresponds to each one. So this blue shaded region here, so the sort of blue area, to do that, we're going to have to integrate. This is going to start from that -1, and it's going to go up to that +1. So it's going to be from -1 to 1. Notice that on this piece, the cubic is on top. So we're going to have x cubed minus 3x squared plus 2x plus 1 minus the curve that is on the bottom here, which is the linear component, which is at 3x minus 2 dx. Then the red area, things are going to flip. The red area is going to be the integral from 1 up to 3. So if the x bounds are from there to there. Now the linear piece is on top and the cubic is on bottom. So it's going to be 3x minus 2 minus x cubed minus 3x squared plus 2x plus 1 dx. And of course, the overall area is going to be the sum of both of these. So we're going to have to sum those up. Now, these are integrals, so we'll have to go ahead and do both of them. But hopefully you guys can see here that since we had that extra intersection and the top curve became the bottom curve, we actually have to have 2 separate integrals. And we have to combine these to get the overall area here. All right, so let's go ahead and do that blue one, I guess. So the blue area here, we can go ahead and simplify a little bit. It's the integral from -1 to 1. X cubed minus 3x squared minus x plus 3 dx, which then looks like you're going to get 1/4 x to the 4th minus x cubed minus 1/2 x squared plus 3x, just a bunch of power rules, evaluated from -1 to 1. And then we get 1/4 minus 1 minus 1/2 plus 3. That's plugging in the 1. And then plugging in the -1, we get 1/4 plus 1 minus 1/2 minus 3. Now, notice some things are going to be pretty clean. This is going to cancel with this. This is going to cancel with this. And we're going to get that -1 minus 1, so that's -2. 3 plus 3, that's 6. So we're going to get a 4 there. All right, now let's think about that red area. Now, if you're pretty comfortable with your sort of, your geometry and your graph here, you probably have a guess about what this red area is here, right? Visually, we can sort of see that these things do look pretty symmetric, and in fact, they are perfectly symmetric here. So the area actually in here is equivalent to 4, and the overall area is just going to be 8. Now, if you're a little unsure, or maybe these things are not perfectly symmetric, you would need to do the other integral separately. So in this case, I'm going to just go ahead and do the integral to show you guys that in this case they are symmetric, but that is not always a rule, right? Just because you have two regions doesn't mean that they're guaranteed to be two symmetric regions. This case they are, but that's just a special coincidence. Well, let's go ahead and just check. We'll actually go ahead and do this. So let's simplify it first. It's going to be the integral from 1 to 3. Looks like we're going to have minus x cubed plus 3x squared plus x and then minus 3 dx, which we can integrate as minus 1/4 x to the 4th plus x cubed plus 1/2 x squared minus 3x, evaluated from 1 to 3. We can plug in the 3, and it looks like we get 3 to the 4th, which is 81. So we get negative 81 over 4, plus a 27, plus a 9 halves, minus a 9. And then we get minus a minus 1/4 plus 1, plus 1/2, minus 3. So a little bit of messy stuff, but we can go ahead and do this. This is going to be 18 over 4, and negative 81 and 18 over 4. That sounds like negative 63 over 4, if I'm correct. Negative 63 over 4. And then looks like we get plus 18. And then over here, we can combine this stuff together. And then that looks like we're going to get a 1/4. And then a minus 2, looks like, overall. Yep. And then we put this stuff together. Minus 63 over 4, minus 1/4. That's going to be minus 64 over 4, which sounds like minus 16. So this is going to become minus 16 plus 18 plus 2, which indeed is 4. Like we said, they were symmetric, so we got 4 for both. So that means that the sort of overall area is 4 plus 4, which is going to be 8 there. So there we go. The overall area of this region was equivalent to 8. So there we go. A couple examples of determining the area the area of a region formed by several curves. In our next video, we'll be finishing up section 6.1 by taking a look at another example or two, but as well as also taking a look at how to integrate with respect to y and visualize these things not by filling them in as vertical components like we have been, but instead actually viewing them as being filled in by horizontal components, which we'll be integrating with respect to y. So we'll take a look at that in our next video.